Have you ever thought about numbers having a secret code? Like a hidden structure, kind of like a fingerprint that's totally unique to each one? Well, today, we're going to crack that code.
Yeah, I'm serious. It's kind of like asking, do numbers have their own DNA? And the answer is, surprisingly, yes. And the key to it all, it's a special group of numbers that are basically the building blocks for every other number out there. You guessed it, prime numbers. So here's the plan. We'll start with the alphabet of this code, the primes. Then we'll check out the rulebook, which is called the Fundamental Theorem. We'll see how it works in a practical way. And then, get this, we'll use it to solve an ancient mystery. It's going to be awesome. Okay, so let's dive in. To get a handle on this secret code, we first need to get familiar with its alphabet. And a great way to think about it is that prime numbers are like the atoms of math.
So you've got two main types of numbers. On one side, you have the primes. Those are our atoms. They're the basic indivisible bits. Then you have composite numbers, which are more like molecules. They're just made by sticking those prime atoms together. So a number like 253, it's not just 253. It's really a molecule built from an atom of 11 and an atom of 23. Pretty cool, right?
Okay, so if primes are atoms, you'd expect there to be some rules for how they combine, right? I mean, there has to be. And there are. That's exactly what the Fundamental Theorem of Arithmetic is. It's basically the official rulebook for our secret code.
And here's the rule itself. It's got two super important parts. First, it tells us that any composite number can be broken down into a product of primes. Okay, cool. But the second part, that's where the real magic happens. It says that that specific combination of primes is totally 100% unique.
Let's make this a little more concrete. Take a big, kind of clunky number like 32,760. It seems complicated, but its prime DNA is actually pretty simple. It's just 3 2s, 2 3s, a 5, a 7, and a 13 all multiplied together. And get this, no other combination of prime numbers will ever give you 32,760. It is a one-of-a-kind mathematical fingerprint. And the guy we have to thank for being so sure about this amazing rule, that's Carl Friedrich Gauss. I mean, the idea itself had been floating around since ancient Greece with Euclid, but Gauss, they called him the Prince of Mathematicians. He was the one who finally nailed down the proof once and for all.
So you might be thinking, okay, this is a neat theory, but is it actually useful? And the answer is a big yes. In fact, if you've ever been in a math class and had to find the highest common factor or lowest common multiple, well, you were actually using this theorem, even if you didn't realize it. It turns out that using these prime factors makes finding those things super easy. Here's how it works. First, you just break down each number into its prime DNA. For the highest common factor, the HCF, you just look at the prime factors they share and grab the smallest amount of each one. For the lowest common multiple, the LCM, you do the opposite. You look at all the prime factors from both numbers and grab the biggest amount of each. Simple as that.
Okay, let's try it with 6 and 20. First, the HCF. What primes do they have in common? Just the number 2. The smallest power is just 1, 2. So the HCF is 2. Easy. Now for the LCM. We look at all the primes we see, 2, 3, and 5. We take the biggest power of each. For 2, that's 2 of them, 2 squared. For 3, it's just 1. And for 5, it's just 1. So you multiply 2 squared times 3 times 5, and boom, you get 60. It's such a clean way to do it.
Okay, that's the practical stuff. But now, let's ramp it up a notch. We're going to take this idea and use it to solve a genuine ancient mystery that stumped mathematicians for ages. The big question is, can this secret code of prime numbers actually prove that a number is irrational? So just as a quick reminder, what's an irrational number? It's basically any number you can't write as a simple fraction, p over q. Think of pi or the square root of 3. Their decimals just go on and on forever without any repeating pattern. And the most famous of them all is probably the square root of 2. Now to prove this, we need a really clever logical tool called proof by contradiction. The strategy is kind of brilliant. You basically pretend to be a detective who starts by assuming the opposite of what you're trying to prove is true. Then you follow the logical clues step by step. If you end up at a place that's totally impossible, a contradiction, well, that means your first assumption had to be wrong. All right, let's put on our detective hats. We're going to use this exact method, along with our secret code theorem, to finally crack the case of the square root of 2. Step 1. Assume the opposite. So let's just say for a minute that the square root of 2 is a rational number. That means we should be able to write it as a simple fraction, a over b. And this is important. We're going to assume that fraction is already simplified all the way down, meaning a and b don't share any common factors. Okay, step 2. We just do a little bit of algebra. Let's square both sides of that equation. That gets us 2 equals a squared divided by b squared. Now to get rid of that fraction, let's just multiply both sides by b squared. And that leaves us with this really important equation. 2 times b squared equals a squared.
Now hang on, this is the first big clue. Look at that equation. If a squared is equal to 2 times something, that means a squared has to be an even number, right? And this is where our fundamental theorem comes in. Because of the uniqueness of prime factors, if a squared is even, then the original number a must also be even. That's a huge piece of the puzzle.
Okay, so let's follow that lead. If a is an even number, we can just say it's equal to 2 times some other number. We'll just call it c. Now let's plug that back into our main equation. A little bit of simplification, and we get a brand new equation. B squared equals 2 times c squared.
Whoa, wait a second. Do you see that? It's the exact same situation we had before, but now it's for the number b. If b squared equals 2 times something, then b squared has to be even. And if b squared is even, then b itself must be even too.
And gotcha. That's the contradiction. That's the impossible situation we were looking for. We just proved that a has to be even and that b has to be even. So they both share a common factor of 2. But hold on, remember what we said at the very beginning? We assumed our fraction a over b was already simplified. It can't have a common factor. So because our initial assumption led us straight into a logical paradox, that assumption has to be wrong. It's impossible. The square root of 2 simply cannot be written as a fraction, and therefore, it must be irrational. Case closed. So that was pretty intense, right? But let's zoom out for a second. Why is this theorem called fundamental? I mean, what's the big deal here? Here's why it's so important. It proves that the entire universe of numbers isn't just a random jumble. There's a beautiful, elegant structure hidden just beneath the surface. Every single number has its own unique, unchangeable prime fingerprint. And that uniqueness isn't just a fun fact. It's the key that unlocks some of the deepest truths in all of mathematics. It is, without a doubt, a cornerstone of how we understand numbers. I mean, it's just amazing to think that such a simple idea, that every number has a unique prime code, can lead us to such a profound and powerful conclusion. It really makes you stop and wonder, doesn't it? What other incredible secrets are just hiding there, in plain sight, waiting for us to find the right key?